Our galactic neighbor hides a universe of the bizarre. The Large Magellanic Cloud is not just a fuzzy patch of light. It is a cosmic laboratory where the laws of physics seem to bend. By the end of this journey, you will see this familiar dwarf galaxy in a completely new and unsettling light. We are going to explore 25 of its strangest phenomena, from stellar ghosts and runaway stars to gravitational enigmas that challenge everything we know. What awaits is a catalogue of cosmic oddities, including a nebula that looks like a crime scene and the ghost of a galactic collision written in the stars. What do you think is the most fundamental rule of our universe that could be broken out there? This journey begins in a place of both breathtaking beauty and cosmic violence. Nestled within the Large Magellanic Cloud is a stellar factory of unimaginable scale, the Tarantula Nebula. To call it a nebula almost feels like an understatement. If it were placed at the same distance as the Orion Nebula in our own galaxy, it would cast shadows on Earth and dominate the night sky. This is the largest, most active star-forming region in our entire local group of galaxies, a seething cauldron of gas and radiation where stars are born at a ferocious rate. The strange part is not just its size, but what it is creating at its very core. Deep within its glowing filaments, like a spider at the heart of a web, lies a dense cluster of newborn stars known as R136. This is where the rules of star formation are broken. Inside this cluster, astronomers have found stars so monstrously huge they defy belief. We are talking about stellar behemoths weighing over 250 times the mass of our own Sun. Think about that for a moment. Our Sun is already massive enough to hold the entire solar system in its gravitational grip. These stars are 250 of those, crushed into a single, ferocious ball of nuclear fire. Their existence is a profound puzzle. Our best models of how stars form suggested there was a natural upper limit, a point where the radiation pressure from a newborn star would blow away the very material feeding its growth. Yet here they are, these cosmic titans, shining with the brightness of millions of suns and living fast, furious lives. They are destined for cataclysmic ends, not as ordinary supernova, but as potential hypernova, explosions so powerful they could outshine entire galaxies and seed the cosmos with heavy elements. Looking at images from the Hubble and James Webb Space Telescopes, the Tarantula Nebula does not look like a peaceful nursery. It looks chaotic, turbulent, a web of glowing gas shredded by stellar winds from these infant giants. It is less a cradle and more a volatile crime scene, where the evidence of a violent, ongoing birth is written across light years of space in brilliant hues of red and blue. The violence of those stellar births is only a prelude to their spectacular ends. In 1987, astronomers witnessed the final, explosive death of one of the Large Magellanic Cloud's massive stars, an event that became known as supernova 1987A. For the first time in centuries, a star in our cosmic neighborhood detonated, and we had the telescopes to watch. The light from that explosion took 160,000 years to reach Earth, but when it arrived, it offered an unprecedented front-row seat to stellar death. The star that died, known as SK-69202, was a blue supergiant, and its demise created a remnant that continues to puzzle scientists today. At the heart of that expanding debris field, something strange is happening. Observations from the Hubble Space Telescope have revealed a mysterious, glowing knot of material, a blob that is not behaving like the rest of the remnant. This object is racing away from the center of the explosion at an almost incomprehensible speed of over 7 million kilometers per hour. That is fast enough to travel from Earth to the Moon in about 3.5 minutes. What could this high-speed fugitive be? One compelling theory suggests it is a literal chunk of the original star itself, a piece of the stellar core that was violently ejected during the supernova, surviving the blast and now fleeing the scene. Another, even more thrilling possibility is that this glowing knot is not just a chunk of debris, but a newborn compact object like a neutron star that received a tremendous kick from the asymmetrical explosion. This would be like a cosmic cannon firing a city-sized ball of ultra-dense matter across the galaxy. The hunt for the true nature of this runaway object is tied to another great mystery of supernova 1987A. At the center of the beautiful, intricate rings of gas that now surround the remnant, astronomers have been listening intently for the telltale, rapid-fire radio beacon of a pulsar, the spinning neutron star that should have been left behind. So far, there is only silence. This absence is as puzzling as the runaway blob. Did the core collapse into a black hole instead, leaving no pulsar to find? Or is the pulsar there, hidden or obscured by the thick debris, its beam of radiation not yet pointing toward Earth? The story of this supernova is far from over. It is an active crime scene with evidence still being analyzed and a central suspect, the stellar remnant, still missing. Every new observation brings us closer to understanding the chaotic physics of a star's final moments and the strange objects that can be hurled into the void in the process. That runaway knot of debris is a stark reminder that a supernova's violence shapes space for millennia, but not all stellar deaths leave such chaotic crime scenes. Some carve out structures of haunting, almost impossible beauty. Within another vast nebula complex in the Large Magellanic Cloud, known as N44, lies a perfect cosmic ghost. Astronomers call it N44F, and in telescope images, it appears as a stunningly spherical, delicate bubble of glowing gas, floating in the darkness like a celestial jellyfish. Its symmetry is so precise it looks manufactured, a fragile glass ornament blown by the breath of a star. This ghostly sphere was not created by a sudden supernova explosion, but by a slower, persistent force. At its heart lies a massive, hot star burning furiously. For its entire short life, this star has been blasting its surroundings with a hurricane of charged particles, a stellar wind moving at millions of kilometers per hour. Think of it like a cosmic sandblaster, relentlessly pushing against the surrounding cloud of cold gas and dust from which it was born. Over thousands of years, that relentless pressure has hollowed out a cavity, sweeping the material into a thin, glowing shell that we see as this perfect bubble. The puzzle is not how it formed, but why it is so perfectly round. In the turbulent, messy environment of a star-forming nebula, you would expect bumps, ripples, and asymmetries. The fact that this bubble is a near-perfect sphere suggests the star's wind has been remarkably steady, and the cloud it expanded into was surprisingly uniform. It is a snapshot of a delicate balance between a star's outgoing fury and the resisting pressure of the interstellar medium. But even this ghost has a flaw, a clue to its environment. On one side of the sphere, the shell appears to have burst open. It looks like a bubble that has been pressed against a wall, creating a blowout where the hot gas from inside is now streaming into a darker, denser region beyond. This tells us the bubble is not floating in empty space. It has expanded until it hit a wall of much denser material on one side, and the pressure was too great. The shell ruptured, and the stellar wind now has an escape route like steam from a kettle. This single, beautiful object tells a layered story. Its perfect roundness speaks to a long period of stable, powerful stellar output. Its one ruptured side is a diary entry about a collision with an invisible obstacle in the cosmic dark. When you place an image of N44F next to the tangled, chaotic remnant of a typical supernova, the contrast could not be sharper. One is the product of a sudden, violent death, the other the signature of a long, forceful life. Both are graves for massive stars, yet they leave behind monuments of completely different character. This ghostly bubble makes you wonder what other perfectly shaped structures are hiding in the chaos, waiting to be read like cosmic fingerprints. That ghostly bubble of gas is a monument carved by starlight, but not all structures in the Large Magellanic Cloud are so luminous. Cutting a dark swath across its bright disk is a feature astronomers call the Dark River. From our vantage point, it appears as a vast, winding lane of absolute blackness, a serpentine void that seems to swallow the light of millions of background stars. This is not an empty gap in the galaxy. It is the opposite. The Dark River is an immense, dense cloud of cosmic soot and ice, a frigid structure so thick with microscopic dust grains that visible light cannot penetrate it. Think of it as a mountain range seen in silhouette against a sunset, but on a scale spanning hundreds of light years. Every pinprick of light it blots out is a distant sun, its story temporarily hidden from our view. This river of dust is far more than an obstacle. It is a crucial component of the galactic ecosystem, a cold, dark womb where future stars are conceived. Within its deepest, most shielded pockets, gravity works in silence, pulling together knots of gas and dust so dense they begin to collapse. Here, hidden from our optical telescopes, protostars are igniting, wrapped in thick cocoons of their own making. To witness this hidden birth, we must change our perspective. We have to look with different eyes. Infrared telescopes like the James Webb Space Telescope are the perfect tools for this. Infrared light, with its longer wavelengths, can slip between the dust grains that block visible light. Much like heat from a stove can be felt even if the stove itself is hidden behind a curtain. In infrared images, the terrifying Black River transforms. It glows with a faint, warm light, revealing the intricate filaments and dense cores within. The dark silhouette becomes a vibrant, complex landscape, bustling with hidden activity. What makes this dust even stranger is its fundamental composition. The Large Magellanic Cloud is what astronomers call metal-poor, meaning it contains fewer elements heavier than hydrogen and helium compared to our Milky Way. Those heavier elements, forged in stellar furnaces and scattered by supernova, are the building blocks of dust grains, so the soot of the Dark River is not the same as the dust in our own galaxy. It is likely more primitive, composed of different ratios of carbon, silicates, and ices. This alters how it absorbs light, how it clumps together, and how it shields forming stars. We are essentially studying a different recipe for cosmic dust, one that harks back to an earlier era of the universe, so this dark river is a dual mystery. It is a veil hiding the stellar generations behind it, and it is a cryptic ingredient list written in a language of ancient chemistry we are still learning to read. The very thing that obscures our view is also the cradle for the galaxy's future. The dark river of dust gives way to regions where light has violently reclaimed its territory. Within the glowing expanse of a nebula catalogued as LHA 120N180b, we find a structure that looks less like a cloud and more like a diagram from a physics textbook. This is an immense region of ionized hydrogen, a place where ultraviolet radiation from newborn stars has stripped electrons from countless atoms, making the entire cloud glow with a fierce pinkish red light. But carved deep within this luminous sea are two colossal, nearly spherical voids known as superbubbles. Each of these cavities spans dozens of light years, vast enough to swallow our entire local stellar neighborhood whole. They were not formed by a single event. Imagine a family of massive stars being born, living their short, furious lives, and then dying in supernova explosions, one after another, over millions of years. Each star during its life blows a fierce wind of particles. Each supernova delivers a titanic shockwave. Together, this relentless barrage from multiple stellar generations acts like a cosmic jackhammer, excavating the surrounding gas and sculpting these gigantic hollows. The strangeness here is not their existence but their relationship. These are not two isolated bubbles. They sit side by side, their expanding walls pressing against one another. In detailed observations, you can see the thin shell of gas where their boundaries meet. a shared wall that is being stretched and distorted by the opposing pressures from within each cavity. This makes N180b a perfect natural laboratory. We are watching the process of galactic feedback in real time. The energy and heavy elements from dead stars are literally reshaping their own environment, clearing out space and potentially triggering or suppressing the next round of star formation in the compressed gas along their rims. Their alignment suggests they were born from two separate but adjacent stellar nurseries that are now conversing through these expanding bubbles. One bubble's growth affects the other's shape. Their merged shockwaves travel through the galaxy in complex ways, seeding turbulence and possibly even funneling material to form new, strange structures. This is the life cycle of a galaxy written in glowing gas and empty space, a story where the death of stars directly dictates the conditions for the birth of their successors. Seeing these twin voids makes you realize a galaxy is not a static painting, but a simmering pot, where energy from one event ripples out and stirs the entire mixture. The geometry of those superbubbles is a product of chaotic forces, but some structures in the cloud achieve an almost artificial precision. Far from the turbulent nurseries, a dying star has crafted a masterpiece. In our own Milky Way, one of the most puzzling sights is the Red Rectangle Nebula. It surrounds a dying star, and through our telescopes, it appears not as a blurry sphere, but as a stark geometric form. Its name comes from its distinct rectangular shape and deep crimson color, the result of glowing hydrocarbon molecules. Most strangely, at its heart, detailed images reveal a delicate X-shaped structure, a pattern of concentric rungs that looks like a cosmic ladder sealed inside a jewel box. For decades, this object stood alone, a beautiful anomaly whose formation process was debated. Then, astronomers looking at the Large Magellanic Cloud found something astonishing, a near twin. Here, in a galaxy with simpler chemistry, lies the red rectangle's extreme cousin. It shares the same shocking geometric form, the same intense ruby glow from hydrocarbon compounds, but everything about it is amplified. The shape is even more pronounced, the contrast sharper against the blackness of space. Finding this object here is a profound shock to our understanding. The original red rectangle is what we call a post-AGB nebula. It was created in the final, complex throes of a sun-like star, a phase where it pulses and sheds its outer layers in a precise, slow dance. The strange X-shape is thought to be caused by twin jets of material or a dense disk of dust around the star, sculpting the outflow into that iconic form. The key ingredient for the deep red color is those complex hydrocarbon molecules, essentially soot, forming in the cool outer envelopes of the dying star. And that is the problem. The Large Magellanic Cloud is metal-poor. It has fewer of the heavy elements like carbon, oxygen, and silicon needed to form such a rich, complex dust. According to many models, this galaxy's environment should be too primitive, too simple, to produce such an intricate and dust-rich nebula around a dying star. It would be like finding a masterfully crafted Gothic cathedral in the middle of an ancient, sparse wilderness where the necessary stone and tools were thought not to exist. Yet there it is. Its very existence forces a reevaluation. It tells us that even in a more primitive galactic environment, stars can still engineer these complex chemical processes. They can still create the conditions to forge intricate carbon-based dust and then sculpt it with breathtaking symmetry. Seeing these two nebulae side by side is humbling. One is a mystery in our backyard. The other, its distant cousin, deepens the mystery by proving such beauty can arise under conditions we thought were insufficient. It suggests the universe has a hidden preference for geometry, a way of creating order even in the final, dissipating breath of a star. That geometric nebula is a fossil of a star's final breath, but some stellar outbursts leave behind phantoms that move faster than light itself. In 2002, a star in our own Milky Way, V838 Monocerotes, did something inexplicable. It flared with a sudden, immense brilliance, not as a supernova destroying itself, but as a mysterious eruption that left the star intact. As its light raced outward, it began to illuminate vast, concentric shells of dust that had been expelled in earlier, quieter epochs. The result was a ghostly illusion, a so-called light echo, where rings of light appeared to expand outward from the star at speeds that seemed to defy physics, appearing to move faster than light itself across the sky. It was a stunning cosmic magic trick, a three-dimensional structure being painted by a fleeting flash. While V838 Monocerotes is in our galaxy, the Large Magellanic Cloud holds its own collection of these eerie phenomena. Because we know the distance to the cloud with great precision, every light echo discovered there becomes a calibrated scientific instrument. When a variable star in the LMC experiences a similar outburst, its flash travels outward in a perfect sphere. When that sphere of light hits a pre-existing shell or cloud of dust, that dust scatters the light toward us. We see that illuminated patch long after the initial flash has passed. As time passes, we see light from farther and farther along the dust structure, creating the illusion of an expanding ring or shell. It is like standing in a dark cave and watching the beam from a flashlight sweep across distant, complex walls, revealing their shape bit by bit. Studying these echoes in the LMC allows astronomers to do something remarkable. By measuring the apparent expansion rate of the echo and knowing the exact distance, they can perform cosmic trigonometry. They can map the precise three-dimensional architecture of the dust clouds around the star, structures that would otherwise be invisible. More importantly, by analyzing the brightness and color of the echo, they can work backward to calculate the exact energy and nature of the original stellar outburst that caused it. The echo becomes a forensic recording of a stellar tantrum that happened decades or even centuries ago. Time-lapse animations compiled from years of Hubble Space Telescope observations reveal these echoes in action. They show ethereal rings of light swelling outward, not because anything physical is moving that fast, but because a wave of illumination is washing over a frozen landscape of ancient dust. The effect is both beautiful and deeply unsettling, a reminder that what we see in the cosmos is often a delayed broadcast, a message from the past being slowly decoded by the present. Each expanding ring is a chapter in a star's hidden history, now suddenly readable in the faintest glow. Those ghostly echoes are recordings of stellar outbursts, but some of the galaxy's most profound silences speak to a deeper mystery. When astronomers survey the Large Magellanic Cloud, they find a puzzling absence. For a galaxy of its size and age, it should be adorned with dozens of ancient, dense stellar cities known as globular clusters. These are spherical swarms of hundreds of thousands of stars, all born together in the galaxy's violent infancy over 10 billion years ago. Our own Milky Way has about 150 of these ancient relics orbiting it. Yet the Large Magellanic Cloud, our close companion, possesses only a handful. Where did all its old globular clusters go? This is the galaxy's missing population problem. One compelling theory points to a history of galactic violence. The Large Magellanic Cloud is not orbiting the Milky Way in serene isolation. It is locked in a complex gravitational dance with our galaxy and its own smaller companion, the Small Magellanic Cloud. Over billions of years, these close encounters create immense tidal forces, gravitational pulls that can stretch and shred entire star systems. It is possible that many of the Large Magellanic Cloud's original globular clusters were torn apart during these cosmic close calls, their stars scattered into the galaxy's general halo, lost in the crowd. Another possibility is more fundamental. Perhaps the Large Magellanic Cloud simply formed differently from the start. Its early conditions, its particular mix of gas and dark matter, might have favored the birth of fewer of these immense bound clusters. The galaxy's entire history of star formation might have been more piecemeal, creating smaller groups that did not survive the eons. The clusters that did survive, however, are now treasures that tell their own strange stories. Look at a globular cluster like NGC 1846. Through powerful telescopes, it appears as a classic, dense ball of ancient stars, but detailed analysis reveals an anomaly. Within this single, tightly bound cluster, astronomers have identified two distinct populations of stars. They are not all the same age. There is the expected ancient population, but mixed in is a second group of stars that formed significantly later, perhaps by 1 or 2 billion years. How is this possible? In a globular cluster, all the raw gas for making stars should have been used up in one initial, furious burst. The presence of a second generation suggests that somehow, long after the cluster's birth, a fresh infusion of gas found its way into the cluster's core, triggering a delayed wave of star formation. Where did this new gas come from? It could have been captured as the cluster plowed through a dense cloud in the galaxy, or it might have been provided by the violent winds from aging stars within the cluster itself. This double population makes NGC 1846 a cosmic Russian nesting doll, a relic that contains its own more recent history sealed inside, so the mystery of the missing clusters is twofold. We must explain a grand, galactic-scale absence while also deciphering the complex, layered lives of the precious few that remain. Each surviving globular cluster is not just a simple fossil, but a detailed diary with missing pages, its story intertwined with the turbulent history of its parent galaxy. The ancient, layered histories of globular clusters stand in stark contrast to a region of pure, youthful fire. In the far ultraviolet eyes of telescopes like Galactic, a section of the Large Magellanic Cloud burns with an almost painful blue intensity. Astronomers call it simply the blue blob. This isn't the soft glow of a single nebula or the tight ball of a star cluster. It is a sprawling, seething complex of star formation, a blister on the face of the galaxy where thousands of brilliant hot stars have ignited in a furious, coordinated burst. Their combined ultraviolet radiation, invisible to our eyes but screaming in the data, paints this entire region as a single, brilliant azure stain. The strangeness lies in its scale and synchronicity. This isn't a random sprinkling of new stars. The evidence suggests that across an area spanning hundreds of light years, the star-forming machinery switched on nearly at once. It's as if a vast stretch of the galactic countryside was doused in cosmic gasoline and a single match was tossed in. So what provided the spark? The leading suspects are all agents of cosmic violence. One possibility is a colossal collision. The Large Magellanic Cloud is swimming through a halo of diffuse gas surrounding the Milky Way. If this particular region plowed into an especially dense knot of that intergalactic material, the resulting shockwave could have compressed gas clouds across a wide area, triggering collapse everywhere at once. Another suspect is a chain reaction from the dead. A powerful supernova from an earlier generation of stars could have sent a titanic shockwave plowing through the interstellar medium for millennia, piling up gas into dense sheets and filaments ripe for collapse long after the original star died. Finally, the ever-present tug of the Milky Way itself could be the culprit. The tidal forces from our galaxy, flexing the LMC during a close pass, might have stirred the gas on a galactic scale, creating just the right conditions for a synchronized starburst. This phenomenon, a starburst region, is a crucial engine of galactic evolution. These brilliant blue blobs are factories for heavy elements. The massive stars born within them live fast, die young, and explode, seeding their surroundings with newly forged carbon, oxygen, iron, and silicon, the very stuff of planets and life. The fierce radiation and stellar winds from these hot stars also blow colossal bubbles and shred remaining gas clouds, simultaneously ending one era of star formation while potentially triggering the next along the compressed edges of those bubbles. The blue blob is not a static picture. It is a snapshot of a galaxy modifying its own DNA. In this brilliant ultraviolet stain, we see a wave of transformation sweeping through, a sudden infusion of energy and metals that will alter the chemical makeup and physical structure of that part of the galaxy for billions of years. It is a dramatic reminder that galaxies don't evolve in a steady, gentle glow, but in fits and starts punctuated by these brilliant blue-hot flashes of creative violence. The brilliant chaos of the blue blob is not an isolated event, but part of a larger story written in the very shape of the galaxy. Look closely at images of the Large Magellanic Cloud, and you will notice something is off. This is not a perfect, flat spiral disk like our Milky Way. Its structure is visibly lopsided and warped, as if it were a vinyl record left too close to a heat source. The central bar of stars and gas is not symmetrically placed in the middle, and one side of the galactic disk appears twisted and pulled upward. This distorted form is not a trick of perspective. It is the ghost of a cataclysmic event, the lingering scar from a galactic collision. Hundreds of millions of years ago, astronomers believed the Large Magellanic Cloud had a violent, close encounter with its smaller companion, the Small Magellanic Cloud. The gravitational forces involved in such a near miss are almost unimaginable. Think of it not as two solid bodies crashing, but as two vast swarms of stars passing through each other, their combined gravity acting like a colossal hand reaching in and violently kneading their shapes. Sophisticated computer simulations recreate this ancient drama. They show the smaller galaxy like a bullet tearing through the outer regions of the larger one. The orderly rotation of the LMC's disk is violently disrupted. Stars and gas are pulled out of their flat plane, creating that permanent warp and twist we see today. The central bar is shaken loose from its stable anchor, left drifting off-center, but the collision did more than just bend the galaxy. It stirred the pot on a cosmic scale. Immense clouds of gas that were once placid were sent sloshing and crashing into one another. This sudden, widespread compression became the ultimate trigger for star formation, likely sparking many of the intense stellar nurseries and brilliant blue regions we see across the cloud. The violence of that encounter may have also torn out the galaxy's very lifeblood. Stretching for over 100,000 light-years across the southern sky, invisible to our eyes but clear to radio telescopes, is a vast, faint ribbon of hydrogen gas called the Magellanic Stream. This is a river of raw star-making material flowing through the emptiness between the galaxies. The leading theory is that this immense stream was ripped out from both Magellanic Clouds during their close encounter and subsequent gravitational tug-of-war with the Milky Way. So the ghost of the collision is present in three forms: the twisted body of the galaxy itself, the burst of stellar birth it ignited, and the long, trailing wound of lost gas. The LMC's strange shape is not a static feature. It is a fossilized moment of impact, a snapshot of galactic violence frozen in time, reminding us that even these island universes are not isolated. They interact, collide, and reshape each other, writing their histories in warped starlight and rivers of lost matter. That galactic collision left scars, but it also forged monsters. Deep in the twisted heart of the Large Magellanic Cloud, some of the most violent relationships in the universe play out in absolute darkness. These are the X-ray binaries, cosmic duos where a normal star is locked in a fatal dance with a stellar corpse, a neutron star, or a black hole. Here, gravity writes a brutal script. The dense corpse's immense pull strips gas directly from the atmosphere of its living companion. This stolen material doesn't fall quietly. It spirals down at nearly the speed of light, forming a superheated disk of plasma that glows not with visible light, but with a searing, penetrating fury of X-rays. The cloud is strangely rich with these high-energy predators, and each one has its own terrifying personality. Take LMC X1, for instance. This is a persistent, roaring beacon of X-rays. It is a confirmed black hole binary where a star perhaps 20 times the mass of our Sun is being slowly consumed by a black hole over 10 times more massive than the Sun. We cannot see the black hole itself, of course, but we see the consequences, the intense, flickering X-ray glow from the multimillion-degree disk of doomed matter just outside its point of no return. Then there are the bursters. These systems, often involving a neutron star, operate in a cycle of tense quiet and sudden, violent eruption. Material from the donor star builds up on the neutron star's incredibly dense surface. For hours or days, pressure and heat silently increase. Then, in a flash, the accumulated layer undergoes runaway nuclear fusion, detonating in a thermonuclear blast that, for a few seconds, can outshine our entire Sun across the entire X-ray spectrum. It is a stellar scale bomb triggered by a teaspoon of neutron star material weighing more than a mountain. The true value of finding these systems in the Large Magellanic Cloud, however, lies in a single precious number: distance. In our own Milky Way, calculating the exact distance to an object is notoriously tricky. Dust obscures our view and measurements can be uncertain, but we know the distance to the LMC with remarkable precision, about 160,000 light-years. This turns the entire galaxy into a perfectly calibrated laboratory. When we see an X-ray source there, we can calculate its true, intrinsic luminosity, not just its apparent brightness. And this is where things get truly strange. Some of these X-ray binaries in the cloud are not just bright, they are impossibly bright. They belong to a class called ultraluminous X-ray sources, or ULCs. Their X-ray output is hundreds to thousands of times greater than what should be possible from a typical stellar mass black hole feeding on a star. The radiation is so intense it should theoretically blow away the very disk of material that fuels it, like a hurricane scattering the leaves it needs to breathe. So what are they? One leading, thrilling possibility is that ULXs are powered by the long-sought intermediate mass black holes, cosmic missing links with masses hundreds or thousands of times that of our Sun, heavier than a dead star but lighter than the monsters at the centers of galaxies. Another theory suggests they might be ordinary stellar black holes feeding at a supercritical, messy rate, with radiation punching out in focused beams. The LMC's known distance lets us weigh these monsters accurately, and the answer is pushing the boundaries of physics. Each flicker and burst from these dark duos is a data point in an extreme experiment, testing how matter behaves under the most intense gravitational fields imaginable, far from the safety of Earth. Those dark duos feed in silence, but their final acts can leave echoes that collide. In a quiet corner of the Large Magellanic Cloud, a structure called DML316 presents a beautiful cosmic puzzle. Through the lens of the Chandra X-ray Observatory, it appears as two distinct, delicate bubbles of glowing gas, each a shell-like remnant from a titanic supernova explosion. They float in space like two cosmic soap bubbles that have drifted together, their edges gently touching, creating a shared, shimmering boundary. This is not a single, chaotic blast zone, but a pair of stellar graves placed in intimate proximity. The immediate, breathtaking question is one of relationship. Are we looking at a tragic coincidence where two unrelated stars, separated by light years and millennia, just happened to die in the same patch of sky, their remnants now expanding into one another? Or is this evidence of a far more intimate stellar drama? The second, more thrilling possibility is that these two bubbles are the final testament to a binary star system, two stars born together, orbiting each other for millions of years, that ultimately exploded in tandem. If true, this would make DML316 a rare supernova factory, a single location that produced two cataclysms from a bound pair. To solve the mystery, astronomers become cosmic chemists, analyzing the light from the glowing gas in each bubble. Different types of supernova forge different elemental fingerprints. A Type Ia supernova, the thermonuclear detonation of a white dwarf star, produces immense amounts of iron and nickel. A core collapse supernova, the explosive death of a single massive star, is richer in oxygen, neon, and silicon. By reading these chemical signatures, we can determine what kind of star died in each bubble. The data from DML316 reveals a fascinating split. One of the shells shows the chemical signature of a core collapse supernova, filled with the elements forged in the life and death of a single massive star. The other shell, however, appears to be rich in iron, a hallmark of a Type I explosion. This is a crucial clue. It suggests the two bubbles are indeed the products of two fundamentally different kinds of stellar death. This makes the binary star system theory less likely, as two stars in a bound pair would typically be similar in mass and age, and thus would be expected to die in similar ways. The evidence leans toward a cosmic coincidence, a chance alignment of two unrelated remnants at different stages of expansion. Yet, the fact that their shells are now interacting is itself a rare and valuable event. As the shockwaves from each remnant collide at that shared boundary, they re-energize the gas, heat it to extreme temperatures, and create complex structures. Watching this interaction teaches us how these titanic waves of energy propagate through space, how they mix different batches of chemically enriched material, and how they ultimately recycle the elements for future generations of stars and planets. So DML316 may not be a factory from a single stellar family, but it is a spectacular crossroads. It is a place where the separate stories of two unrelated stars have now converged, their final chapters merging into a single, glowing text for us to read. Deep within the wreckage of a stellar explosion, a cosmic lighthouse is having violent seizures. The pulsar known as pulsar J0537-6910 spins with dizzying speed, completing a full rotation every 16 milliseconds. That is over 60 times a second, a blur of motion where its surface, if you could stand on it, would be moving at a significant fraction of the speed of light. But this neutron star's true claim to fame is not just its speed, but its instability. It holds the record for the highest known glitch rate of any pulsar we have observed. A glitch is a sudden, tiny increase in the pulsar's spin frequency. After spinning down with predictable clockwork precision for months or years, the star suddenly, without warning, spins a fraction of a percent faster. For pulsar J0537-6910, these events are not rare anomalies. They are a regular part of its existence, happening with startling predictability roughly every 2 years. So what is happening inside this ultra-dense corpse to cause these starquakes? The leading theories plunge us into a realm of physics we can never replicate on Earth. A neutron star is not a simple, solid ball. Its interior is a layered nightmare of exotic states of matter. Think of it as having a brittle, crystalline crust of iron nuclei floating on an ocean of superfluid neutrons, a bizarre substance that flows with zero friction. As the pulsar's rotation gradually slows due to magnetic braking, its solid crust slows down with it, but the superfluid interior, because it has no friction, wants to keep spinning at its original, faster rate. Stress builds up between the slowing crust and the faster spinning superfluid beneath it. Eventually, something has to give. In one model, the crust itself fractures in a starquake, a seismic event on a planetary scale that suddenly makes the star more compact. Like a spinning ice skater pulling in their arms, this contraction causes the star to spin faster. In another model, the vortices in the superfluid neutron ocean, which are normally pinned to the crust, suddenly become unpinned and transfer their rotational momentum to the crust in a sudden rush. Either way, the result is a glitch. The incredible regularity of this pulsar's glitches is a gift to physicists. It provides a scheduled experiment in extreme matter, offering a direct probe into the interactions between a neutron star's crust and its mysterious quantum interior. Each glitch is a telegram from a place where matter is crushed to densities greater than an atomic nucleus, and the message is written in the precise timing of radio pulses. This stellar remnant is also a fugitive. The supernova that created it was almost certainly asymmetrical, giving the newborn neutron star a powerful kick. PSR J0537-6910 is now a runaway, racing through the interstellar medium of the Large Magellanic Cloud at hundreds of kilometers per second. As it plows through space, its powerful magnetic field and particle wind slam into surrounding gas, creating a bow shock ahead of it and a trailing wake of energized particles. We see it fleeing the scene of its own violent birth, a hyper-dense, hyper-fast, and hyper-unstable beacon, ticking and jerking its way across the galaxy. The erratic heartbeat of that runaway pulsar is a tiny tremor compared to the immense, invisible forces shaping its entire galaxy. Surrounding the visible stars and glowing gas of the Large Magellanic Cloud is a ghost, a vast spherical halo of dark matter that may weigh 10 times more than all the galaxy's luminous material combined. We cannot see this halo, but we can feel its gravitational grip. By measuring how fast stars and gas clouds orbit the galaxy's center, astronomers can calculate the total mass required to hold everything together. The answer is always the same: there is far more mass than we can account for with stars and gas alone. This missing mass, this dark matter halo, is the hidden scaffolding upon which the galaxy is built. But the size and weight of this ghostly scaffold are now at the center of a heated cosmic debate. Recent, precise measurements suggest the LMC's dark matter halo is astonishingly massive, perhaps 1/10 the mass of the entire Milky Way's halo. This would make it not a lightweight companion, but a heavyweight contender, a dwarf galaxy in name only. If true, this changes the entire story of our local cosmic neighborhood. An LMC this massive would not be a mere satellite passively orbiting our galaxy. It would be a significant partner, its gravity violently shaking the Milky Way's own halo of stars and dark matter as it swings by. Astronomers searching for subtle ripples in the outer fringes of our galaxy's star distribution believe they are seeing the aftermath of this exact collision, the wake left by a heavy dwarf plowing through dark matter. This is the heavy hypothesis. The Large Magellanic Cloud is a bull in a china shop, its passage permanently distorting our galaxy's shape. Yet other lines of evidence introduce troubling doubts. Sophisticated computer simulations that model the dance of galaxies, incorporating dark matter and the laws of gravity, sometimes struggle to produce an LMC as massive as the measurements suggest. In these virtual universes, a dwarf galaxy that heavy would have been torn apart long ago by the Milky Way's far greater gravity, or its orbit would look different than what we observe. This conflict forces a profound question. Is our measurement of the cloud's dark matter halo correct, revealing it as a surprisingly dense and resilient galaxy that is challenging our simulations? Or are the simulations pointing to a flaw in our understanding of how dark matter behaves, or how galaxies interact over billions of years? This is not an abstract puzzle. The outcome reshapes our origin story. If the LMC is truly this heavy, it implies that our Milky Way has recently, in cosmic terms, absorbed a major galaxy, a dramatic event that would have sparked bursts of star formation and scattered stars far from their birthplaces. If the models are correct and the LMC is lighter, then the ripples in our galaxy's halo must be explained by something else, perhaps a more ancient collision we have yet to identify. At its heart, this controversy is about more than one galaxy's weight. It is a direct test of our core theories of dark matter and cosmic structure. The Large Magellanic Cloud, in all its visible strangeness, is also a laboratory for the invisible. Its true mass is a number that could either confirm the dark matter framework we have built, or send us back to the drawing board to confront an even deeper layer of mystery. The true weight of its dark matter halo is written in the stars it has stolen. Wrapped around the visible body of the Large Magellanic Cloud like faint, dissolving smoke rings are the ghostly remains of its own ancient crimes. Astronomers call these structures stellar streams, and they are the fossilized records of galactic cannibalism. Long ago, even smaller dwarf galaxies, drawn in by the LMC's gravity, ventured too close. They were not merely bumped or warped, they were utterly torn apart. Their stars were stripped away in great tidal tails, smeared into elongated ribbons that now orbit silently within the LMC's halo. These streams are so faint and diffuse that they are invisible to the naked eye, even through most telescopes. Detecting them requires painstaking surveys, mapping the precise positions and motions of millions of individual stars to find those moving in concert against the flow. It is cosmic archaeology, sifting through the galactic soil to find artifacts from a forgotten past. Identifying one of these fossil streams is like finding a vein of distinct ore in a mountain. The stars within it will share a unique chemical fingerprint, a specific ratio of elements like iron, magnesium, and carbon that differs from the native stars of the LMC. This signature is a dead giveaway, a tag that says these stars were forged in a different stellar nursery within a different galactic system billions of years ago. By tracing the stream's path and modeling its orbit, astronomers can work backward. They can estimate when the merger happened, how massive the victim galaxy was, and even the angle of the fatal encounter. Each faint stream is a chapter in the LMC's violent autobiography, revealing that its growth, like that of all large galaxies, came not just from birthing stars but from consuming its neighbors. This process, called hierarchical growth, is a cornerstone of our understanding of the universe. We believe large galaxies are built over time from the merging of smaller ones. We see the grand, final acts of this drama in the distant universe, where colossal spirals smash together. But the fossil streams in the LMC let us study the intimate, small-scale details of this process happening right in our backyard. They show us what the early, building block stages of galaxy formation look like, frozen in time. Artist conceptions help visualize this ancient violence. A tiny, irregular dwarf galaxy, like a stellar firefly, approaches the brighter disk of the LMC. Tendrils of gravitational force reach out, pulling the smaller galaxy into a long, thin strand. Its stars are scattered, no longer a coherent family, but now just another component of the larger galaxy's halo. This is not a fast, explosive collision, but a slow, gravitational digestion that can take billions of years to complete. Finding these streams does more than just recount history. It tests the very models of dark matter itself. The shape, density, and survival time of a stellar stream are exquisitely sensitive to the distribution of the invisible dark matter halo surrounding the LMC. A smooth, spherical halo will shepherd a stream into one kind of orbit. A lumpy, clumpy halo filled with smaller dark matter subhalos will chop and kink the stream, leaving visible scars. By comparing the pristine, curved lines of the fossil streams we observe to supercomputer simulations, astronomers can infer the texture of the dark matter environment. So these faint trails of orphaned stars are more than fossils. They are probes, delicate instruments mapping the invisible gravitational landscape of their captor galaxy. They tell a story of past violence while simultaneously revealing the hidden hand that orchestrated it, a ghost writing its history with stolen starlight. Those fossil streams are the legacy of ancient mergers, but one star in the cloud is writing its own violent history in real time. In the constellation Dorado, a star designated R71 is a ticking time bomb of cosmic proportions. It belongs to a rare and unstable class of stellar behemoths known as luminous blue variables. Think of these not as normal stars, but as hypergiants in a state of perpetual, feverish crisis. They are the most massive stars we know of, so luminous and bloated that their own gravity struggles to hold them together. R71 is a prime example of this stellar extremism. For most of its life, it burns with a fierce blue-white light, but its stability is an illusion. Every few decades, something inside this star snaps. It undergoes a colossal eruption, not an explosion that destroys it, but a monstrous stellar tantrum. During these events, R71 can increase its brightness by a factor of 100, temporarily becoming one of the most luminous stars in the entire Large Magellanic Cloud. The cause is a catastrophic loss of self-control. The star's outer layers, heated by ferocious radiation pressure from the core, become unbound. It violently ejects a shell of material weighing several times the mass of our entire Sun, hurling it into space at thousands of kilometers per second. This is not a gentle shedding of gas, it is a stellar hemorrhage. After the eruption, the star contracts and cools slightly, appearing redder and dimmer for a time, before the internal pressure builds again toward another inevitable outburst. Astronomers track this dramatic life through a light curve, a graph of the star's brightness over time. For R71, this graph looks nothing like the steady line of a normal star. It is a seismic readout with sudden, jagged peaks representing each giant eruption, followed by long, slow declines. Surrounding the star is the physical evidence of its past rages, a complex, expanding nebula of its own ejected material. This nebula is not a remnant from a final death, but a growing collection of shrapnel from repeated near-death experiences. This bizarre phase is thought to be a brief, transitional stage in the life of a star over 100 times the mass of our Sun. A luminous blue variable is a star wrestling with its own inevitable fate. It is burning through its nuclear fuel at a reckless pace, and the intense radiation is literally pushing its atmosphere away. The eruptions may be a desperate mechanism to shed enough mass so the star can stabilize, or they may be the final chaotic throes before the ultimate catastrophe. Many astronomers believe that after a few more of these violent outbursts, R71 will end its life not with a whimper, but with a very specific kind of bang, a type in supernova. This occurs when the doomed star finally collapses, but its explosion slams into the dense, slow-moving shells of material it ejected during its LBV phase. The collision creates a supernova that shines brighter and longer than normal, its light echoing through its own pre-existing nebula. So R71 is not just a weird star. It is a star in the process of constructing its own funeral shroud, layer by violent layer. We are watching a preview of its death, a series of dress rehearsals for the final apocalyptic act. The violent instability of a star like R71 is a local drama, but it echoes a chapter from the universe's fiery infancy. Scattered across the deep fields of the Large Magellanic Cloud are tiny, brilliant knots that look utterly out of place. They are not grand spirals or elegant nebulae, but compact, almost blisteringly bright regions of star formation. When viewed through specific filters that isolate the light of doubly ionized oxygen, they glow with a distinct, vivid green hue. To astronomers, these are uncanny replicas, local analogues of the infamous green pea galaxies. The original green peas were discovered not in our neighborhood, but in the extreme depths of the universe as they appeared over 10 billion years ago. They are small, chaotic galaxies undergoing an explosive burst of star formation, and their intense oxygen emission paints them as tiny green dots in telescope images. Finding such similar objects right next door in the LMC is like discovering a living fossil from the cosmic dawn in our own backyard. The key to their strange color is a specific physical process. Inside these dense knots, thousands of newborn massive stars are pumping out a torrent of ultraviolet radiation. This energetic light slams into the surrounding gas, stripping electrons from oxygen atoms with incredible efficiency. When those electrons recombine, they emit light at very specific wavelengths, including a strong line in the green part of the spectrum. In the full color palette of the universe, this brilliant oxygen signal acts like a highlighter, marking regions of extreme stellar youth and ferocious energy output. So why are these local green pea analogues so valuable? They act as a bridge across time. The genuine green pea galaxies in the early universe are so distant they appear as unresolved blurs. We can measure their overall light and chemistry, but we cannot see their internal structure. We cannot distinguish individual star clusters from the surrounding gas or map how the furious radiation from newborn stars is interacting with its environment. This is where the LMC's versions become a Rosetta Stone. Because they are in our galactic backyard, we can point our most powerful telescopes like Hubble and James Webb directly at them and resolve incredible detail. We can see the individual stellar clusters powering the glow. We can trace how their fierce winds are carving bubbles and shredding clouds. We can measure the gradients in temperature and density across the region. In essence, we can dissect the detailed physics of a starburst in high definition. Studying these nearby knots allows astronomers to construct a precise blueprint for the feedback processes at work, how star formation fuels its own quenching by blowing away its raw materials. We can then apply that blueprint to interpret the faint, blurred green dots from the early universe with far greater confidence. They tell us that the tumultuous, productive conditions of the universe's first galaxies are not a lost art. The same basic recipe, dense gas, rapid collapse, and the birth of massive stars, is still cooking in isolated pockets of our neighboring galaxy. These greenish blobs are more than just curiosities, they are time machines. By analyzing their well-resolved chaos, we are learning to read the faded, distant script of cosmic infancy, one brilliant green letter at a time. The brilliant green knots of starlight are echoes of creation, but the death of a star can carve a tomb of shocking asymmetry. In the southern constellation Dorado, the supernova remnant N49 blazes with the aftermath of violence. This is one of the brightest such remnants in the entire Large Magellanic Cloud, a tangled web of glowing filaments that stretches across 75 light-years. Yet for all its brilliance, it looks wrong. Unlike the delicate, spherical bubbles we have seen elsewhere, N49 is a lopsided, chaotic mess. Its shape is not a clean shell, but a ragged, twisted knot of gas, brighter and more complex on one side than the other. It looks less like an expanding bubble and more like a cloud that slammed into an invisible wall. And that is precisely the clue. Astronomers believe the supernova's blast wave, expanding uniformly at first, plowed into a dense, uneven cloud of interstellar material on one flank. The collision abruptly slowed and compressed the shock wave on that side, heating the gas to extreme temperatures and lighting it up in a brilliant, tangled snarl of filaments visible in optical and X-ray light. The rest of the blast wave, encountering less resistance, kept expanding more freely, creating the remnant's unbalanced, teardrop-like appearance. This cosmic collision zone tells us the star did not die in empty space, but within a complex, clumpy environment it helped create during its own lifetime. But the story of N49 holds an even stranger secret, one hidden in the silent, searing glow of X-rays. Data from the Chandra X-ray Observatory reveals a tiny, incredibly powerful point source of energy embedded within the remnant's gas. This is not a random hotspot. It is a magnetar officially known as SGR 0525-66. A magnetar is a neutron star born in a supernova, but with a terrifying twist. It possesses a magnetic field 1,000 trillion times stronger than Earth. It is the most powerful type of magnet in the universe. This dense stellar corpse, only about 12 miles across, emits occasional bursts of gamma rays and X-rays as its unimaginably powerful magnetic field twists and fractures its own crystalline crust. The profound mystery is its location. This magnetar is not sitting at the geometric center of the remnant's gas cloud. It is displaced, offset toward one edge. This is the smoking gun for an asymmetrical explosion. When the progenitor star's core collapsed, the detonation likely did not happen with perfect uniformity. A powerful jet of material or an imbalance in the neutrino flow could have acted like a rocket engine, giving the newborn neutron star a tremendous kick at its birth. It was shot out of the center like a cannonball, and it has been traveling through its own expanding debris field ever since. So N49 presents us with two interlocking puzzles written in gas and gravity. The lopsided shell maps a death in a crowded neighborhood where the blast wave hit a literal wall. The off-center magnetar records the violent, off-balance physics of the core collapse itself. Together, they show that a star's final moment is not a simple, symmetric flash, but a messy, directional event that can send its own dense heart fleeing into the darkness, trailing a wreckage of glowing gas shaped by the obstacles in its path. That lopsided supernova remnant hints at a chaotic death, but the galaxy itself seems to be hiding evidence of the stars that should be dying. When astronomers take a census of the Large Magellanic Cloud stellar population, they find a puzzling demographic gap. There is a notable shortage of red supergiants. These are the final, dramatic phase for many massive stars. After burning through the hydrogen in their cores, these stars swell to monstrous proportions, becoming cool, bloated behemoths hundreds of times the diameter of our Sun. They are the cosmic prelude to a core collapse supernova. In our own Milky Way, we see plenty of these crimson giants, but in the LMC, the numbers do not quite add up. It is as if a crucial chapter in the life story of massive stars is being skipped or edited out. This missing population is more than just a curiosity. It is a direct challenge to our models of stellar evolution. The leading suspect is the galaxy's fundamental chemistry. Remember, the Large Magellanic Cloud is metal-poor. It has a lower abundance of elements heavier than hydrogen and helium compared to our home galaxy. This simpler chemical recipe seems to change how massive stars live and die. In a low-metal environment, a star's outer layers are more transparent. The fierce radiation from its core can escape more easily, resulting in less of a puffing-up effect. The star retains a more compact, hotter form. The theory suggests that many massive stars in the LMC may bypass the extended red supergiant phase entirely. Instead of swelling into a cool giant, they shed their outer layers through powerful winds while still hot and blue, transitioning directly into a Wolf-Rayet star, a searing, naked stellar core shrouded in a nebula of its own ejected material. This would explain the shortage of red supergiants and the relative abundance of Wolf-Rayet stars we do observe in the cloud. But there is another, more practical possibility. Perhaps the red supergiants are not missing at all. Maybe we just cannot see them. These cool, bloated stars are prolific factories of dust. In their vast, extended atmospheres, carbon and silicon atoms can condense into microscopic grains, forming a shroud of soot around the star. In a galaxy already rich with interstellar dust lanes, this self-made veil could be obscuring many red supergiants from our optical telescopes, hiding them in plain sight. They would be glowing embers buried in thick cosmic smoke. Surveys using infrared telescopes which can peer through dust are crucial to solving this. If they find a host of hidden red giants, the mystery shifts from stellar evolution to one of simple observation. The answer carries weight far beyond cataloging stars. The red supergiant phase is the final checkpoint before a supernova. If stars in metal-poor galaxies like the LMC are skipping this phase, it changes what we expect to see when they die. It alters the predicted rates and even the types of supernova that should light up such galaxies. A star that dies as a Wolf-Rayet star leads to a different kind of explosion than one that dies as a red supergiant. This demographic puzzle forces us to ask whether our understanding of stellar life cycles, built largely on observations within our metal-rich Milky Way, is universally applicable. The Large Magellanic Cloud is showing us that a galaxy's chemical identity can rewrite the very script of stellar birth, life, and death. The galaxy's missing red supergiants are a demographic puzzle, but the Milky Way's gravity is solving a different one by pulling the Large Magellanic Cloud apart. Stretching far beyond its visible disk is a faint, sprawling river of stars slowly being torn away. This is the stellar tidal tail, a ghostly extension predicted by every simulation of the galaxy's fateful dance with our own. Just as the Moon's gravity tugs at Earth's oceans to create tides, the Milky Way's immense pull creates gravitational tides on a galactic scale. It is stretching the LMC, drawing out long streamers of stars and gas from its outer fringes. The most famous result is the vast Magellanic Stream, that ribbon of hydrogen gas arching across the sky. But the stellar tail is its elusive counterpart, a river of suns, not gas, that was stripped out alongside it. Finding this river of stars is one of modern astronomy's great observational challenges. These stars are not clustered together in a bright, obvious ribbon. They are desperately faint, spread over an enormous area of sky, and drowned out by the foreground stars of our own Milky Way. It is like trying to spot a single, specific grain of sand on a vast, well-lit beach. Yet hunting for them is crucial because these stellar fugitives hold precise orbital records. Their positions and motions are a perfect tracer of the gravitational forces that pulled them free. By mapping where these stars are and how they move, astronomers can reconstruct the exact path the LMC has taken around the Milky Way over billions of years. They can weigh the Milky Way's dark matter halo with new precision, because the strength of the tides that stripped these stars depends directly on our galaxy's total mass. Wide-field sky surveys are the tools for this cosmic detective work. Projects like the Gaia Space Observatory are meticulously charting the positions and motions of over 1 billion stars. Within that immense dataset, scientists search for subtle grouping stars moving together through space at the same speed and direction, all sharing the distinct chemical fingerprint of the LMC's origin. It is painstaking statistical archaeology. Every confirmed member star is a data point in a three-dimensional map of destruction. Illustrations of this process are both beautiful and violent. They show the Large Magellanic Cloud not as a static island, but as a comet-like shape with long, faint tendrils of stars streaming ahead and behind it along its orbital path. This is the galaxy in the act of dissolving. The stellar tidal tail is more than just debris, it is a timeline. The stars closest to the LMC were stripped most recently. Those farther out, deeper into the tail, were ripped away in encounters that happened long ago. Reading this timeline lets us date the major gravitational shocks in the galaxy's history. So this faint, almost invisible structure is a living record. It confirms the dynamic, destructive relationship between our galaxy and its largest companion, proving they are not just passing neighbors, but intimately connected players in a slow-motion merger that has already begun. That faint stellar tail is a slow dissolution, but the galaxy has also fired a cannonball. Streaking through the halo of our own Milky Way is a star named He 0437-5439, a solitary traveler moving at over 700 kilometers per second. At that speed, it is not just fast, it is unbound, carrying enough velocity to escape the gravitational pull of our galaxy entirely. It is a hypervelocity star, a cosmic fugitive on a one-way trip into the intergalactic void. For years, its origin was a profound mystery. Where could such a star have gotten such an impossible kick? Astronomers became cosmic detectives, tracing its path backward through space. The trajectory pointed like an arrow not to the center of our Milky Way, the usual source of such stars, but out into deep space toward the Large Magellanic Cloud. The evidence suggested this star was not born in our galaxy at all. It was a projectile fired from our neighbor. The only force in nature capable of launching a star at such a speed is the immense gravity of a supermassive black hole. In our own galaxy, we see stars flung from the vicinity of Sagittarius, a star, the 4 million solar mass black hole at the Milky Way's heart. The leading theory for He 0437-5439's origin involves a similar but even more dramatic gravitational slingshot. Imagine a triple star system, 3 suns orbiting one another, drifting too close to a massive, compact object in the heart of the Large Magellanic Cloud. In a chaotic gravitational dance, one of the stars is captured by the black hole's gravity, while the other two are hurled away as a binary pair at a significant fraction of the speed of light. During this frantic escape, the two stars in the binary are so close they actually merge, creating a single, massive blue star that continues its headlong flight, the object we see today. This elegant, if violent, scenario solves multiple puzzles. It explains the star's incredible speed, its trajectory from the LMC, and even its unusual youthfulness. The merger event would have refreshed its outer layers, making it appear younger than it truly is. This story, however, creates a new and deeper mystery. It implies the Large Magellanic Cloud must harbor a central, massive black hole of its own to serve as the cosmic catapult. For a galaxy of its size, this is not a given. The LMC is a dwarf irregular galaxy, and many such galaxies show no clear evidence of a central supermassive black hole. Finding one would reshape our understanding of the galaxy's structure and history. Is there a dark heart lurking in its core, hidden by gas and dust waiting to be revealed? The hypervelocity star is a piece of circumstantial evidence, a smoking gun pointing back to a crime scene we have not yet seen. It turns the LMC from a passive subject of our observation into an active participant, capable of violent acts that send its stars screaming across the cosmic ocean toward us. This one star, a lonely speck of light in our sky, is a messenger. Its speed tells a tale of a close brush with a gravitational monster, and its path points directly back to a hidden power at the center of the galaxy next door. That hypervelocity star is a testament to immense gravitational forces, but some of the galaxy's heaviest structures seem to defy their own purpose. Deep within the cold, dark lanes of the Large Magellanic Cloud, radio telescopes have mapped out dense congregations of molecular gas clouds that should, by all rights, be bustling stellar nurseries. In our own Milky Way, clouds with similar density and chemical signatures are vibrant cradles, glowing with the light of newborn stars. Yet here, these clouds are eerily quiet. They are rich in molecules like carbon monoxide, the classic tracer of star-forming material, but they show no signs of the telltale infrared glow of protostars or the energetic outflows that accompany birth. They are, for all intents and purposes, starless. This presents a fundamental puzzle. What puts a dense cloud of star-making fuel into a state of suspended animation? The answer may lie in the galaxy's unique environment. The Large Magellanic Cloud's lower metal content means its cosmic gas clouds are different. Metals elements heavier than hydrogen and helium act as crucial coolants. When a cloud begins to collapse under its own gravity, these heavier elements radiate heat away into space, allowing the cloud to contract further and fragment into the dense cores that become stars. In the metal-poor clouds of the LMC, this cooling process is less efficient. The clouds stay warmer internally, and that extra thermal pressure acts as a support against gravitational collapse. It is like comparing two blocks of clay, one cold and firm, the other warm and soft. The cold block shatters easily into many pieces under pressure, while the warm one just deforms. The LMC's clouds are the warm clay resisting fragmentation. Another missing ingredient could be a trigger. In our galaxy, star formation is often jump-started by a shockwave, the blast from a nearby supernova, or the collision of two gas streams. These shocks compress the gas violently, pushing it over the edge into gravitational collapse. The quieter, less turbulent environment of some LMC regions might lack these catalytic events, leaving the clouds in a stable but sterile equilibrium. There is also the hidden hand of magnetic fields. Threaded through these clouds are lines of magnetic force that can provide additional support, acting like a network of cosmic springs that hold the gas apart. If the magnetic fields in these particular clouds are especially strong, they could be effectively pinning the gas in place, preventing it from clumping together into stars. So these starless clouds are not failures, they are reservoirs holding onto their precious fuel. They represent the quiet before the storm in the grand cycle of galactic life. Astronomers suspect they are in a pre-stellar phase, slowly accumulating mass or waiting for the right disturbance, a passing shockwave from a distant supernova, the tidal pull from a galactic encounter, or the gradual loss of magnetic support to tip the balance. When that happens, the quiet will end in a burst of creation. Studying them is like watching a forest after a long winter, the seeds present and the soil fertile, but awaiting the precise combination of warmth and rain to sprout. These dark, silent clouds remind us that star formation is not an automatic process. It is a delicate threshold requiring a specific recipe of cold temperatures, high density, and a nudge from the universe. In the Large Magellanic Cloud, we see that recipe being prepared but not yet cooked, offering a rare glimpse into the long, quiet gestation that precedes a galaxy's brightest moments. The quiet, starless clouds are monuments to potential, but the galaxy's gravitational influence may extend to objects so faint they barely exist. Recent deep sky surveys have begun to reveal hints of the ultimate cosmic ghosts, possible ultra-diffuse galaxies hiding in the Large Magellanic Cloud's own backyard. Imagine a galaxy the size of our Milky Way, spanning 100,000 light-years across. Now, imagine that instead of containing hundreds of billions of stars, it holds only a few billion or even less. Its stars are so sparsely scattered that the galaxy is almost transparent, a wispy smear of light so faint it gets lost in the glow of the night sky itself. These are ultra-diffuse galaxies, and finding them orbiting the LMC would be a discovery that reshapes our understanding of small-scale cosmic structure. The search for these phantoms is a monumental challenge. Astronomers must meticulously scan vast areas around the LMC, using the most sensitive telescopes to pick out these faint, extended smudges from the background noise and the dense foreground of Milky Way stars. It is like trying to spot a single, faint candle flame through a dense, foggy window while a bright street lamp shines nearby. The candidate objects that have been identified are so ethereal that their stars contribute almost no mass. This leads to the startling conclusion that these galaxies, if confirmed, must be absolutely dominated by dark matter. Their visible stars are just a few tracers, like lone buoys floating on the surface of a vast, invisible ocean of mysterious matter. Their sheer size with so few stars suggests their dark matter halos are unusually spread out and fluffy, preventing gas from cooling and condensing to form many suns. Their presence as satellites of the Large Magellanic Cloud would complete a crucial hierarchy. Just as the Milky Way has satellite galaxies like the LMC, and the LMC has smaller companions like the Small Magellanic Cloud, finding ultra-diffuse galaxies would show that the LMC itself has its own tiny entourage. This nested system would be a perfect miniature of cosmic structure, a galaxy with its own galaxies. Simulated images of such a scene are haunting. They show the familiar, barred shape of the LMC, bright and detailed. And just off to its side, almost merging with the black of space, is a vast circular haze, a pale, milky patch with only a handful of discernible star clusters. It looks less like a galaxy and more like the ghost of one, a faint breath on a cold windowpane. Confirming these objects would provide an extreme test for galaxy formation theories. How does a dark matter halo grow so large yet form so few stars? Does the environment around the LMC somehow suppress star formation in these satellites, or were they born this way, relics from an era when galaxies were inherently more diffuse? Each candidate is a natural experiment probing the lower limits of galaxy formation. Finding them would mean the Large Magellanic Cloud is not just a collection of strange phenomena within its borders, but a gravitational anchor for an entire hidden system of the universe's faintest islands, completing its portrait as a dominant force in our local celestial sea. The silent, ghostly satellites of the Large Magellanic Cloud watch over a stellar drama that once captivated the world. In late 2019, the familiar red supergiant Betelgeuse, the shoulder of Orion, began to fade. Over months, its light dimmed by a staggering 65%, a dramatic change visible even to the naked eye. The astronomical community buzzed with speculation. Was this the prelude to a supernova? The eventual explanation was more subtle. The star had belched out a colossal cloud of dust which cooled and condensed, partially blocking our view. But while all eyes were on Orion, a far more dramatic dimming was unfolding unnoticed in our neighboring galaxy. A red supergiant in the Large Magellanic Cloud, a star we might call WOHS 281, experienced a dimming event so profound it makes Betelgeuse's fade look like a minor flicker. This distant giant, a true twin to Betelgeuse in size and temperament, saw its visible light output plunge by over 90%. For a time, it nearly vanished from optical telescopes. The sheer scale of this event presents a monumental puzzle. The cause could mirror the Betelgeuse scenario, but amplified to an extreme. Perhaps WOHS 281 experienced a truly titanic eruption, ejecting a dust cloud of incomprehensible scale, one so vast and dense it shrouded the entire star. Another possibility points to a radical change in the star itself. The surface of a red supergiant is a bubbling, unstable cauldron. Massive convective cells, like boiling granules the size of solar systems, can bring hotter material up from below or allow cooler patches to dominate. What if a temporary but global shift in this churning dynamo caused the star's surface temperature to drop significantly over a vast area? A cooler surface emits less visible light, which could explain the dimming without any dust at all. Here is where the Large Magellanic Cloud provides an irreplaceable laboratory. In our own galaxy, calculating the true brightness of a star like Betelgeuse is fraught with uncertainty. Its distance is not perfectly known, and interstellar dust between us and it can muddy the measurements. But for a star in the LMC, we have a gift, a known distance. Every star in that galaxy is, for all intents and purposes, the same distance from us, about 160,000 light-years away. This removes a massive variable. When we see a star there dim, we can calculate the exact intrinsic change in its luminosity with far greater confidence. We are not fooled by foreground dust or distance errors. Studying WOHS 281's great dimming gives us a clean, controlled experiment in the late-stage tantrums of dying stars. By comparing its detailed light curve and subsequent recovery to Betelgeuse's, we can test models of mass loss, dust formation, and stellar instability in a metal-poor environment. This singular event in a neighboring galaxy transforms a celestial curiosity into a precise diagnostic tool, helping us decipher the final, feverish breaths of stars destined to soon vanish in a flash that will, one day, outshine their entire home galaxy. These 25 strange phenomena are not isolated curiosities. Together, they form a single, profound portrait of the Large Magellanic Cloud as the universe's ultimate cosmic laboratory. Here, the unusual is not the exception, it is the standard operating procedure. Every glowing nebula, every runaway star, every silent dark cloud is a data point in a grand experiment, testing the laws of physics under conditions we cannot replicate on Earth. From the hypervelocity stars shot from hidden black holes to the ghostly streams of cannibalized galaxies, each mystery is a piece of a larger puzzle. By studying this one small, warped galaxy next door, we are not just cataloging its oddities, we are learning the fundamental language of how all galaxies are born, live, and evolve. We see how chemistry dictates stellar life cycles, how gravity writes history in twisted starlight, and how dark matter sculpts the invisible foundations of reality. The LMC's proximity gives us a front-row seat to the universe's most extreme processes, offering clarity we could never find in the blur of distant, ancient galaxies. So the next time you look up at the Magellanic Clouds, remember, you are not just seeing fuzzy patches of light. You are looking at a frontier of the unknown, a dynamic and violent workshop where the cosmos forges its future. Which of these 25 phenomena fascinated you the most? Was it the ghostly bubbles, the unstable pulsar, or the hidden rivers of dark matter? Let us know in the comments below and subscribe to join us for more deep dives into the profound mysteries of space.